Today we're going to be starting our unit on rational functions. Today we are going to simplify, multiply, and divide rational expressions. So by the end of this video, you should be able to use factoring to simplify, multiply, and divide rational expressions and be able to find the domain of a rational expression. First of all, a rational expression will look like a fraction. A rational number means the number can be written as a fraction, so a rational expression is also a fractional expression. A rational expression is in simplified form provided that its numerator and denominator have no common factors other than 1. So it's just like simplifying fractions. You need to make sure that you cancel out any common factors. Therefore, to simplify rational expressions, we need to divide out common factors. If we're going to divide common factors, the first step is to factor. If you don't remember how to factor, then you need to go back to the quadratics unit and rewatch those videos on factoring. Since we are never allowed to divide by 0, we need to state the domain. So we are going to simplify these two rational expressions here. The first thing we need to do is factor the numerator and factor the denominator. So x squared minus 81, if you remember, that is a difference of perfect squares, will factor to be x minus 9 and x plus 9. The denominator is a linear expression, so all we can do is factor out a GCF, which is 2. Then we can cancel any common factors. So we can cancel out the x minus 9 because both the numerator and denominator have x minus 9. So then our final answer will be x plus 9 over 2. When we state the domain, we need to look at the original denominator of the function before we started canceling things. When we state the domain, we need to look at the original expression before we started canceling. So I'm going to use 2 times x minus 9. And we discussed this a little bit when we did composition of functions. To find the domain, you need to set the denominator equal to 0 and solve for x. So if we have x minus 9 equals 0, we get x equals 9. That means if we plug 9 in, we will end up dividing by 0, which we are not allowed to do. So our domain can be written as x such that x does not equal 9, or if you prefer interval notation, negative infinity to 9, 9 to infinity. Either way is fine. For this second problem, again, we need to start by factoring. So if we factor the numerator, we need to find numbers that multiply to 6 and add up to 5, which are 2 and 3. And then in the denominator, all we can do is factor out a GCF of x squared. Again, we need to cancel any common factors, which in this case, the only common factor is x plus 3. And so we're left with x plus 2 over x squared as our final answer. Again, to state the domain, you want to use the denominator from before you canceled. So I'm going to use x squared times x plus 3, and I'm going to set that equal to 0. So if I say x squared equals 0 and I solve, I end up with x equals 0. X plus 3 equals 0, and solve, you end up with x equals negative 3. So when we write out our domain, x cannot be 0 or -3. Both of those would make us divide by 0, which we are not allowed to do. So you can either write this in set notation, x, such that x does not equal -3 or 0, or you can write it in interval notation. But since we have two different numbers, we'll have to say -infinity to -3, -3 to 0, and 0 to infinity. So if you have a lot of domain restrictions or a lot of numbers that x cannot equal, set notation will be more efficient, but it's still your personal preference. Let's take a look at multiplying. First, let's go back to elementary school. If we have 2/3 times 4/5, and we want to multiply these together, we just multiply across. Multiply the numerators together and multiply the denominators together, which in this case would give us 8/15. So it's the same thing even when you have rational expressions. They still follow all of the rules of fractions. But we are going to start by factoring. So the numerator of the first fraction, you can factor out an x. The denominator can be factored into x plus 1 and x plus 1. The numerator of the second fraction can be factored to x plus 1 times x plus 3. And the denominator can factor out an x. So again, we just want to cancel out factors in the numerator and denominator that match. So we have an x plus 3 and an x plus 3 in both the numerator and denominator. We have an x plus 1 in both the numerator and denominator. And we have an x in both the numerator and denominator. So we can go ahead and cancel all of those out. As long as one factor is in the numerator and one's in the denominator and they are identical, we can cancel them. So we are left with x minus 2 over x plus 1. When we do the domain for multiplication problems, we need to look at both denominators. And we are going to set both denominators equal to 0. So if we have, from the first fraction, we have x plus 1 times x plus 1. And from the second fraction, we have x times x plus 3 equals 0. So when you solve these for x, the first denominator gives us x equals -1. The second denominator gives us x equals 0 and -3. So when we write out our domain, I'm just going to write this in set notation because we have several domain restrictions. We have x such that x cannot equal -1, 0, or -3. Because any of those numbers would make one of the denominators equal to 0. Problem number 4 doesn't have much factoring. And it looks like we're really close to being able to cancel out factors, but not quite. Because we have a 12 minus x and an x minus 12. So whenever you have situations like that where they're almost the same but they're just in the wrong order, try to factor out a -1. So if I look at 12 minus x, I can factor out a -1, and then that becomes x minus 12. We can't factor 3, and the denominator of the second fraction is just x minus 12. So then we can cancel our like factors. The 3's cancel because one's in the numerator and one's in the denominator. And the x minus 12's also cancel because one is in the numerator and one is in the denominator. So all we're left with is -1. Again, we need to look at the denominator of both fractions to figure out our domain. The denominator of the first fraction is just 3. So since there are no x's, we will not have any domain restrictions for that fraction. But the second fraction has x minus 12 as its denominator. So if we set that equal to 0, we end up with x equals 12 as our domain restriction. So our domain is x such that x does not equal 12, because that would make us divide by 0. Let's take a look at division. So again, let's go back to elementary school. To divide fractions, if I have 2/3 divided by 4/5, the way I was taught to remember this is keep, change, flip. You keep the first fraction the same, you change the division to multiplication, and you flip the second fraction. Then you just have a multiplication problem, which we already know how to do. You just multiply the numerators together and multiply the denominators together. And you end up with, in this case, 10/12, which can be reduced to 5/6. So dividing rational expressions will follow the same rules. So I'm going to keep this first fraction the same in problem number 6. Then I'm going to change the division to multiplication and flip the second fraction. Then I'll do this just like I did the multiplication problems. I need to factor. X squared cannot be factored. X squared minus 1 is x plus 1, x minus 1. X plus 1 cannot be factored. And 3x is just 3 times x. So now I can cancel out my like factors. The x plus 1's cancel. And then the x in the denominator will cancel with one of the x's in the numerator. So I'm left with an x in the numerator and 3 times x minus 1 in the denominator. Now, the domain for the division problems is a little bit trickier. We need to look at the denominator of the first fraction and both the numerator and denominator of the second fraction. And that's because we have to flip that fraction. So originally the denominator of the second fraction is x plus 1. After we flip it, it becomes 3x. So we need to check all 3 of those parts and see what value for x will make them equal 0. So we need to do the first denominator, which we said factored to x plus 1, x minus 1 equals 0. 3x equals 0, and x plus 1 equals 0. So when we solve all of these, we get x equals -1 and 1, x equals 0, and x equals -1. So we don't need to write the -1 as a domain restriction twice, we can just write it once. So we can just say x such that x does not equal positive or -1, or 0. Let's try number 7. So again, we're going to follow the keep, change, flip rule. We're going to keep the first fraction the same. Change the division to multiplication, and flip the second fraction. Then we need to factor. To factor the numerator of the first fraction, you can use factoring by grouping, you can use the box method, you can use guess and check, you can use whichever method you feel most comfortable with. To factor x squared minus 4, we have x plus 2 and x minus 2. X plus 2 cannot be factored, and you can only factor out a GCF from 4x plus 16. Then we need to cancel our like factors. The x plus 4's cancel, and the x plus 2's cancel. So we are left with 3x plus 1 over 4 times x minus 2. Again, when we do our domain restrictions, we need to look at the denominator of the first fraction and both the numerator and denominator of the second fraction. So we can use the factored form. If we say x plus 2, x minus 2 equals 0, x plus 2 equals 0, and 4 times x plus 4 equals 0. When you solve to find the domain restrictions, you get x equals positive and negative 2, x equals negative 2, and x equals negative 4. So when we write out our domain, we have x such that x does not equal positive or negative 2 or negative 4. Let's look at one more problem. Some problems have both multiplication and division. So the first term can be written as a fraction over 1. Then we are dividing by the second fraction, so we're going to have to flip the second fraction. And then we're multiplying by the third fraction. The third fraction will not get flipped. If there were parentheses here, dividing by that product, then both fractions would be flipped. So let's go ahead and rewrite this. We keep the first fraction, change the division to multiplication, and flip the second fraction. And then multiply by the third fraction. Then we can factor. We have x plus 6, x minus 5 over 1 times x plus 4, x plus 3 over x minus 6, x minus 5 times x minus 6 over x plus 6. Now we can go ahead and cancel our like factors. We have an x minus 5 in both the numerator and denominator, an x minus 6, and an x plus 6. So we are just left with x plus 4 times x plus 3 over 1. And since it's over 1, we do not need to write that denominator, but you can if you feel more comfortable with it. Now for the domain. The first fraction was not originally a fraction, so we don't need to worry about that. We do need to look at both the numerator and denominator of the fraction that we divided by and the denominator of the fraction that we multiplied by. So if we have x plus 4 times x plus 3 equals 0, x minus 6 times x minus 5 equals 0, and x plus 6 equals 0. Our domain restrictions will be negative 4, negative 3, 6, 5, and negative 6. X minus 6, x minus 5 times x minus 6 over x plus 6. Now we can go ahead and cancel our like factors. We have an x minus 5 in both the numerator and denominator, an x minus 6, and an x plus 6. So we are just left with x plus 4 times x plus 3 over 1. And since it's over 1, we do not need to write that denominator, but you can if you feel more comfortable with it. Now for the domain. The first fraction was not originally a fraction, so we don't need to worry about that. We do need to look at both the numerator and denominator of the fraction that we divided by and the denominator of the fraction that we multiplied by. So if we have x plus 4 times x plus 3 equals 0, x minus 6 times x minus 5 equals 0, and x plus 6 equals 0. Our domain restrictions will be -4, -3, 6, 5, and -6. So when we write out our domain, we have x such that x does not equal positive or -6, -4, -3, or 5.